Today's video will be on 6.2, evaluating and graphing polynomial functions, and 6.7, using the fundamental theorem of algebra. So we're going to start off by looking at the general form of any polynomial function. And we know that a is the coefficient, x is our variable. When we have it x raised to the n, and then n minus 1, we know that that's going to be in descending order. So if n was 5, this would be 4, and so forth, until we get down to our constant. When you write the general form, the exponents are all whole numbers and all the coefficients are real numbers. So let's get some vocab down. The leading coefficient is the coefficient of the term with the highest exponent. So no matter how your terms are arranged, you look at the term that has the highest exponent. Whatever coefficient is in front of that is the leading coefficient. The constant term is the term or the number with no variable. The degree is the highest exponent. And again, it doesn't matter where that highest exponent is located. It could be the first term, it could be the last term, because it's not always going to be given to you in standard form. It's whatever term has the highest exponent. That exponential value is the degree of your polynomial function. And last is standard form. And in standard form, your terms are written in descending order, and descending order according to your exponents. And we have different names for each of these polynomials. If the polynomial has a degree of 0, which means there's no variables, that is considered a constant. If it is a first degree, so like y equals 3x plus 5, that is considered a linear equation. If your degree, the highest exponent, is 2, that is a quadratic. If the highest exponent you see is a 3, that means you've got a cubic function. And 4 is a quartic. So just a couple names you should know. Now we're going to talk about the end behavior of a graph. The end behavior is the behavior of the graph as x approaches positive infinity, and that's written as a plus sign with the infinity sign, or a negative infinity. So we're going to look at our first graph. We've got f of x is equal to x, and we know that f of x is the same thing as y. So this is the equation y equals x. We know that this is just a simple equation with a y-intercept of 0 with a slope of 1. So y equals x is going to look like that. We have to describe the end behavior for two pieces. One as our graph approaches positive infinity, and one as it approaches negative infinity. So we're going to write f of x, and again we know f of x is y. We want to find out what does that approach as x approaches a positive infinity. So our x value we know is on the x-axis. As x gets larger, how does our y value, how is that affected? As x gets bigger, so does y, so y is going to approach a positive infinity. Now we've got to do that a second time. What's going to happen to my y value, my f of x, as x approaches a negative infinity? Again, our x value is moving left and right, so as our x values get smaller, it's approaching negative infinity for the y values. Now if we switch it around a little bit, we've got f of x is equal to a negative x. We still have a y-intercept of 0, but we've got a slope of a negative 1 instead of a positive 1. So same thing, we want to see what happens to our f of x. What does that approach as x approaches a positive infinity? So as our x values get larger, our y values are getting smaller. So y is going to approach a negative infinity. So we're going to find out what happens to y as x approaches negative infinity. So as our x values get smaller, we see that our graph is getting larger. So the y-coordinate is approaching a positive infinity. Alright, so that was our two linear examples. Now we have x squared. We know that's a quadratic, that's a parabola with vertex at 0, 0 with a normal shape opening up. So again, we have the end behavior. We've got end behaviors in two directions. So we want to find out what is happening to y as x approaches a positive infinity. So as x gets larger, our y value is going to forever get larger as well. So our f of x, or our y, is going to approach a positive infinity as our x approaches a positive infinity. Now what happens to y as x approaches a negative infinity? So as our x's get smaller, our y values are still getting larger. So y is still going to approach a positive infinity. Alright, our last one for here. What happens to y as x approaches a negative infinity? So we have f of x is equal to a negative x squared. That's a parabola, still vertex of 0, 0, normal shape, but now it's going to be opening down. So as our x values get larger, we see that our y values are approaching a negative infinity. What happens to y as x approaches, oops, that should have been a positive infinity, as a negative infinity? So as x gets smaller, we see that our y's are getting smaller as well, and they are still going to be approaching a negative infinity. So we want to describe the end behavior, what happens to y as x gets bigger and as x gets smaller. So as we turn over to the next page, I want you to use your graphing calculator to graph the following functions and describe the end behavior of each graph. So you're going to type each of these 4 graphs into your calculator. Remember, if you want x to the third, it's x raised to the third power using that caret button. Alright, so I want you to press pause, sketch your graphs, try to describe your end behavior. When you're done, go ahead and press play again. Alright, as you graphed your y equals x to the third, you should have gotten a graph that looks like this, kind of like a little snake or an S shape. As our x values approach negative infinity, so you want to be careful and see what your x values are going to be approaching. Sometimes positive will be on top, sometimes negative will be on the top, doesn't matter, so you've got to pay attention. So as my x values approach negative infinity, as they get smaller, my y values are going down, so y is going to be approaching a negative infinity. As x gets larger, my y values are getting larger as well, so my y is approaching a positive infinity. When we change that to a negative cubic graph, it reflects over the y-axis, so it's going to be opening this way. So as x approaches a negative infinity, so as x gets smaller, we see that our y values are getting larger, so it's going to approach a positive infinity. As x gets bigger, as it approaches a positive infinity, my y values are getting smaller, giving me a negative infinity. When you graphed f of x is equal to x to the fourth power, you may have been surprised. It is a fourth degree quartic polynomial, but it looks kind of like a parabola. Sometimes it'll look a lot different, but in this case it's going to look like a parabola. So as x approaches a negative infinity, as x gets smaller, my y values are approaching a positive infinity. They're getting bigger. As x gets bigger, my y's are getting bigger. So both of those are approaching a positive infinity. And you can kind of guess, once you get to your last graph, you probably are picking up on the pattern. I see that my fourth degree graph is opening down. So whether x is getting smaller or x is getting larger, no matter which way my x is going, both of my y's are pointing down. So my end behavior in both directions are approaching a negative infinity. Now, I think the easiest thing to do when determining the end behavior is put it in your calculator, graph it, and describe what you see. But there is also a summary chart for the end behavior where you don't even have to graph it if you don't want to. If the degree is even, so on the front page we had x squared, on this page we have x to the fourth. So if it's an even degree graph, 2, 4, 6, 8, 10, and so forth, the leading coefficient is positive, both ends of your behavior are going to be approaching a positive infinity. So think about a parabola. If it's opening up, then both ends of the behavior are facing up. So if it's an even degree, so a parabola, and the leading coefficient is negative, so a parabola that's opening down, it's always going to be going down. So both of your end behaviors are going to be negative. Now the hard one is when it's an odd degree. That is your linear equation, that's your cubic, so 1, 3, 5, 7. If it's a positive graph, we are looking at a linear equation with a positive. So as x gets bigger, y gets bigger. As x gets smaller, y gets smaller. And if it's negative, it's just flipped. So as x gets bigger, y gets smaller. As x gets smaller, y gets bigger. So you can use that chart, so if you don't have your calculator on the day of the quiz or something else happens, you don't necessarily have to graph the equation in order to see what the end behavior is. This is going to be true for any odd or any even degree graph. Alright, our last page. How many solutions or zeros should you expect to find? When you are looking at the equation, the degree tells you how many solutions the equation is going to have. So when I look at number 1, x to the 5th minus 7x squared minus 8, I should expect to find 5 solutions because 5 is the highest exponent. For our second one, 9x squared plus 3x minus x to the 4th plus 10 equals 0, we are not going to expect to find 2 solutions. If you pick 2, you were fooled. It's always the highest degree. The degree is the highest exponent among all of them. So in the second one, we should have expected to find 4 solutions. So now we are going to say how many solutions should we expect to find and actually find those solutions. So for number 1, I've got x squared. So I know I should expect to find 2 solutions. If I want to find these solutions, there's a lot of different ways that we could do this. One way is to move the 16 over, so x squared is equal to 16, square root both sides, and we've got x is equal to a positive or negative 4. Or we could have factored. X squared minus 16 is the difference of 2 squares, so we've got x minus 4, x plus 4 equals 0, and again we get the exact same thing. X is equal to 4, x is equal to a negative 4. We've got our 2 solutions that we expected to find because of the degree. And those are 2 real solutions. When we go to number 2, again we've got x squared, so we should expect to find 2 solutions. This one's not as easy. We can't just go ahead and move the 16 to the other side and solve. So we want to factor. So we're looking for 2 numbers that are going to multiply to 25, add to 10. That is 5 and 5. Well, we got the exact same thing, so that's x plus 5 quantities squared. So when we look at here, we've got 1 solution at a negative 5. But we should have expected to find 2. What this is a repeated solution. So we still have 2 solutions. We have 2 real solutions, but because it's repeated, we only have 1 unique solution. So that's kind of an exception to the rule, kind of a trick. So it doesn't really look like there's 2 solutions, but there are. Has a repeated solution, but there's only 1 unique solution. And our last one, number 3, we try to factor it, multiply to 5, add to 3. There's no 2 numbers that are going to multiply to 5 and add to 3, so this is not factorable. But we know we've got lots of different ways to solve a quadratic without factoring. I'm going to use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that gives us a negative 3 plus or minus. Inside, that's going 9 minus 20 gives us a negative 11 over 2. So we have a negative 11 on the inside. If you try plugging that into your calculator, you're going to get an error message. We have an imaginary. We still have 2 solutions, but in this case we've got 2 imaginary solutions. So the degree will tell you how many solutions, but you could have real, you could have imaginary. If you tried graphing that, you wouldn't be able to find those two imaginary solutions. Alright, the last thing for our video, and then we will be done, is writing a polynomial function of least degree that has real coefficients, the given zeros, leading coefficient of 1. Thing is, we want to do two things. Write in intercept form and write in standard form. And this is actually easier than you think. We're going to say that the solutions to our equation are 3, -4, and 5. Given our solutions, we should be able to find our x-intercepts. If I tell you that x equals 3 is a solution, that should tell you that x minus 3 was one of your factors. If I tell you that x is equal to a -4, we move the 4 over, so x plus 4 was a factor. And if x is equal to 5, we know that x minus 5 was a factor. So we're moving backwards. If we go back up to the last portion, we factored, we found x minus 4 was a factor. We solved for x, and we found x was equal to 4. So we're just moving in the opposite direction. So if I tell you x is equal to 3, x minus 3 was a factor, which gives us factored form. F of x is equal to x minus 3, x plus 4, and x minus 5. So that's part 1 of the problem. Part 2 is writing in standard form, and this is going to take us back to our notes from 6.3, is we've got to multiply those three binomials together. So we start with the first two. X times x is x squared. X times 4 is 4x minus 3x minus 12. Don't forget about the x minus 5. We have not multiplied that yet. Combine your like terms. Now we've got a trinomial times a binomial. This is where we've got to use our superfoil. We're going to distribute x to everything. So we've got x cubed plus x squared minus 12x. And then we have to distribute the -5 to everything. So that gives us a -5x squared, a -5x, and a positive 60. From here, our last step is just to combine our like terms. So we have the 1x cubed, a -4x squared, -17x, and a positive 60. Okay, so let's go ahead and do that one more time. For number 2, we've got a solution of 2, which means x minus 2 is our factor. Now it gets a little bit harder when we look at the 4i and the -4i. The only way that we can get 4i and a -4i is if we have imaginary solution. The only way we get imaginary solution is if there's a negative inside of your square root sign. So we've got to think about what number square rooted gives us 4. Hopefully you guys know that's 16. And if there's a negative inside, that'll give us our imaginary. So this is going to come from x squared, x equaling the square root of a -16. That's where the positive 4i and the -4i is going to come from. Well, again, we're going to work backwards. So if before I square rooted, the last thing I would have done is I would have had x squared is equal to a -16. And if we want to solve that for 0, we move the 16 back over. So the factor in this case is going to be x squared plus 16. So our standard form of our equation is x minus 2 times x squared plus 16. And again, each of these pieces, whether they're real or imaginary, are solutions to a factor. If you want to find the factor, you just set the equation equal to 0, so you move the numbers to the other side. When you have the imaginaries, it was coming from taking the square root of a negative number. So there's standard form, there's intercept form. Now we want to go to standard form. Notice that intercept form and factored form are the exact same thing. So to get to our standard form, we've got a FOIL. We've only got two binomials, so x times x squared is x cubed. x times 16 is 16x, a negative 2x squared, and a negative 32. So we don't have a whole lot to do. This is a lot less work than the last one, but you've got to make sure that you rearrange. Standard form is in descending order, so we want to make sure that our pieces are going in the correct order. Don't forget, whatever sign is to the left of the term is going to stay with the term. So when I move that negative 2x squared in front of the 16x, I kept that negative with the 2. Alright, that is it for today's video.